Objective today is going to be to help us understand the relationship between the change in temperature and heat. Understanding that heat has no mass and is also a form of energy. Understanding that energy is the ability to do work, and therefore in thermodynamics what we do is that we look at energy from two points of view. So there are two phases or two paths that we're going to follow. So energy from the pathway of heat energy and energy from the pathway of work, which is going to be related to force, right? Force times acceleration. And in this experiment then, we're exploring the observation of temperature change, which is going to be critical in terms of determining the specific heat. Specific heat is dependent upon the change in temperature and along with the pressure. So those two variables are very important in terms of us determining what specific heat is going to be. We're also looking at heat loss equal heat gain, because we're looking at the transfer of heat from material to the surrounding, and from the surrounding to the material. And so the heat that is being lost by a material should be gained by something else. And so we're going to be looking at that. We're going to be calculating the specific heat, which is going to be focusing on how easily materials absorb or emit, or meaning release heat. Heat is being absorbed or being released, and so we're going to be looking at that as well, because when we talk about heat, we're talking about that chemical energy that is related to your materials. We're looking at some values for specific heat which are high, and some values are low. And this is all based on how easily the material is going to absorb the heat, or how easily the material is going to be losing the heat. Looking at some of the changes and the specific heat of materials. Materials is very important in physics. Thermodynamic covers the heat of the materials. So engineering students are specifically interested in how much heat their materials can absorb. Some materials absorb a lot of heat, and so therefore we can make more use of those materials. For example, if you look at the element of aluminum, aluminum is used for roofing in third world countries, and the purpose is that it's able to absorb a lot of the heat. Then the next thing that we look at is that we need to use a device that is going to measure this change in heat, which is going to be measuring the flow of the heat, but we're going to be using a calorimeter that's going to be measuring that. And then for the use of the calorimeter, we must measure how much heat is released, how much heat is absorbed. As we measure that amount of heat released or absorbed, then we need to represent it by variables, and your variable will be Q. So Q is going to be representing heat absorbed or emitted, meaning release, by the material. And that is going to be including the mass of your material times the specific heat of the material, which is a physical property, times the change in temperature. So as we can see, very dependent upon the change in temperature. So the change in temperature, delta T, is going to be equal to final temperature minus initial temperature. So the difference between the two of them will give you delta T. So the product between the mass and your specific heat or heat capacity is going to be multiplied by the change in temperature, which is then going to be equal to that heat absorbed or heat emitted. Now, what we're going to be looking at also is that we're going to be demonstrating that the heat absorbed is going to have a value of a positive, and the heat emitted or released is going to have a negative value. So when we're looking at heat observed, that's going to be equal to minus the heat released as well. Then if we're going to be finding a specific heat, that's going to be equal, this is C or S can be used, is going to be equal then to Q, which is going to be the heat observed or released, divided by the mass times the change in your temperature. So this is how you're going to be finding that. The units that are going to be used are going to be joules. So we must make sure then that as we carry out this multiplication, our mass in our specific heat and the delta T temperature, which should be in Kelvin, should be able to then correlate to be able to give you joules at the very end when you carry out the calculations. Because we're talking about materials, we also have to include the phase changes. As we mentioned before, phases of matter, everything around us occupies space, and has mass. And what we're going to do here is that we're going to look at how your substance can be transformed into different phases, meaning that you will be looking at a substance in a solid phase, a substance in the liquid phase, a substance in the gas phase. So these three phases, so what we're going to be looking at is how a substance can be converted from one phase into another phase, and this is what we call a physical property. Phase changes are physical property. I think this is matter. Phase changes are physical property, and so as we look at solid going to liquid, liquid going to gas. And so in these phases is where we're going to take a look at a substance that's going to be in a solid phase, and suddenly as the heat is increased, the heat energy. Yes. So your phase changes, solid going to liquid, going to gas, right? So we are familiar with in physics 1, when we look at the phase changes, and in chemistry, how our solid was converted to liquid, and therefore we can follow that conversion by the amount of heat energy that the substance absorbed. And as your substance absorbed that energy, what we did is that we created a graph in which we were able to follow the time or the progress of your reaction versus the temperature. So as your temperature increases, then we find that your solid starts to melt, and then right here we have an equilibrium point, and here the temperature is constant. And then as you increase the temperature once again, you find your substance is going to go through another phase change. So you're going from a solid to a liquid, and then we find that eventually your substance is going to evaporate, right? And that's where you have your gas phase. This is what we call a heating curve. We are familiar with this coming into physics 2. And now we're going to look at a different type of curve, which is going to be called the triple point and critical point. And this one is going to be showing again the solid, liquid, and gas. And we're going to try to bring this up with our projector. So let's see. So this is a diagram that is going to be representing your findings, because the objective of the laboratory is also for you to be able to look at the phase changes, and in which you're going to look at a plot with your y-axis labeled as the pressure and your temperature. Remember we said that the heat is dependent, the specific heat is dependent upon the changes that the temperature and the pressure go through. So here we're looking at the three phases. Where you have a triple point is where the three phases meet. And as you can observe the different phases that we have a solid and we have a liquid phase. You're looking at a horizontal point, which is a critical point as well. And then you're looking at your triple point here, and then you're looking at the vapor phase, and you're looking at a gas phase. And here you see as they pass that critical point, then you're going to go into the supercritical phase, and you're looking at the compressibility of your liquids as well. And so we experimentally, you are trying then to make sure that the material that we're working with is going to be representing either one of these phases that we see here. And so this is specifically then dependent upon us finding the specific heat of your materials. So there is a table that relates to all of the materials that we will be working with in your engineering classes. You're going to be exposed to some of these materials, and you will see that in the handbook of physics and chemistry, we do have listed all the different specific heat of all materials that we are going to be using. So this handbook is what also is going to help you if when you are working and you're looking for that a specific heat of a specific material, so that you can be able then to determine if that material is going to absorb easily heat or is it going to be emitting easily heat. So that's the most important part. We're going to stop here, and then we're going to look at our laboratory and see how is it that we're going to understand the concept and apply to our laboratory setting. This first one is latent heat, and you should have yourself a test tube, and you have a thermometer, a 250 milliliter beaker, a pipette, disposable pipette, and I am using in the laboratory 2 beakers, 1 beaker in which I'm using a hot plate. You will be using a stove top and a pot, and you're going to be boiling some water. I am also using a beaker with ice. I have this in the laboratory. You will be placing your thermometer in the freezer with the water that is going to be at a certain temperature. So this water here, I am going to make this into an ice water, and I'm going to let the thermometer come down to minus 10 degrees Celsius. So when you look at the thermometer, your thermometer must be reading room temperature. And so aside from the room temperature then, based on that, as your guideline, you're going to make sure the thermometer drops to minus 10 degrees. And meanwhile, I have the stove on here, and this is going to be increasing in temperature to make sure then that we have boiling water. So while you are carrying out the one part of the experiment, you should be then using the stove with a pot of water on it, so that can be boiling while you are taking care of the other part of the experiment. So you're being asked to take 1.5 milliliters of water, and that we can, this is, let me see if it's graduated, but this, oh yeah, it has the graduations here. So you have 1, 2, 3, and this will be fitting 5 milliliters, right? So from this is where we're going to then get some of that cold water. So this freezing water, so the first thing we're going to do, this is down to, it still has to go down some more. So we're going to use the pipette, fill test tube with approximately 1.5 milliliter of water. And I'm going to get some water here. And I'm trying to bring that down, so I'm going to be using, whoa, just exactly 1.5. Okay, so we're going to take that, I'm going to put the pipette, that 1 milliliter of water, let's put it down, and it's a temperature should be minus 10 degrees Celsius on your thermometer. And this is not there yet. So let's get that water down to a little bit more ice in there. Okay, so the purpose is to bring down this temperature to minus 10 degrees. And then we're going to place the thermometer in the test tube into a 250 milliliter beaker so that the test tube can rest upright. So I have a test tube rack here. So I don't need to do this. But because you will be doing this at home, you will be needing to place it into the beaker like this, because you have to place a thermometer inside there as well, so that you can be able then to read the temperature of the water to a minus 10 degrees. Remember, you're not touching the thermometer with your entire hand, but you're holding at the tip of the thermometer right here. And then you're being asked to put the beaker with the test tube and thermometer in the freezer and allow 1 hour to completely freeze and reach at least minus 5 degrees. So your goal then is this is already to minus 10. So your goal is to bring this down to minus 5 degrees. So you're going to place it in the freezer for at least 1 hour. Just make sure this is a thermometer that I'm using that is totally different than the one that you have. You will be using a smaller one, which you can be able to handle better, and it will hold up in the freezer. So you are taking a thermometer then in the test tube, in the beaker, and placing this in the freezer for 1 hour. And once that is freeze, you're going to make sure it comes down to a minus 5 degrees. And then after that, you're going to move to the next step. Now, remember that you're making sure that your thermometer must be reading minus 5 degrees. So it must be really, really, very, very low. Then you're going to take the thermometer and the beaker and the test tube out of the freezer. You're recording the temperature of that thermometer. So you have a data table given to you. So the first thing you're going to do is record temperature of, and this will be freezing water. So this is the first part of the experiment where you're going to be looking at table, table 2. Let me just go here and see what other table we have. This is their data sheet, so they're recording this. This is on table 2, temperature and your observation, and then temperature of boiling water over time. I think that this table 1. Just give me 1 minute, just. Okay, because I'm trying to find their table 1. All right. So once you have placed for an hour your beaker with the test tube and the thermometer in the freezer, and it has been there for an hour, then you're going to remove it and you're going to record the temperature of the water. And you're going to, as you record the temperature in the water, I'm going to bring up the table that you're going to be using to do that. And that table, that would be table 2 for you. And actually table 1, sorry, experiment 1 data sheet. So you have table 2, the temperature of your frozen water. So over a period of time, you want to make sure that you record the temperatures temperature at 0 time, what's the temperature, observation. Then you start in 5, what's the observation, 10, 15, 20, 25, and until you get to 30. Make sure you record in full sentences what observation, right, you observe in terms of. Was there an increase? Was there a decrease in the temperature? Because remember, we're looking at what amount of heat will be absorbed or released. Then in the second table, which will be table 3 labeled for you, you're looking at the boiling water. So here with the boiling water, as the water boils, you are reading the thermometer. And as you read the thermometer for this water that has boiled, you are going to record the temperature after 1 minute. So you will let the thermometer in this reading, so you will let the water boil, and then after 1 minute, then you record your temperature. So don't forget to do your timing, right? Either use the time watch or your phone, and make sure that as after 1 minute, you're going to record it. You're going to read the thermometer, and then you're going to record that on this second table right here. And as you do that, then you're going to wait 5 minutes, and you're going to record once again. And this is the table that you have here. So you want the temperature of your boiling water after 1 minute, and the temperature of your boiling water after 5 minutes, and then you're going to record the two of them there. Now at home, you want to make sure that you are very careful in terms of using the stove top, right? Do not touch anything with your hands. Remember that this is very, very hot, so you're going to be using a glove at home or a mitten, so you can be able to remove that if you have to. But if not, just leave the pot there sitting on your stove top. But do not touch anything because it's very, very hot. Do not forget to wear your goggles, right? Do not forget to turn the stove off once you are finished. And do not forget to hold the thermometer from the top, like this, from the tip. Do not hold the thermometer with your hands like this, because you're transferring heat to the thermometer as well. So with the freezing, the freezer, if you have cold water like this, like what I did, then you can use the ice water very cold, making sure your temperature drops to -5 degrees that is required for your first table. And also you're looking at the different intervals which you're going to be doing your readings, making sure once again that you're recording all observations being done. So that's it for today for your latent heat. You are supposed to answer your post questions and making sure that they are related completely to this experiment. Observation of heat energy. Remember that we have learned already how we are mostly interested in how much heat can be absorbed. And so the conservation of energy, the law of conservation of energy tells us that energy is neither created nor destroyed, but is transformed from one form of energy into another. So we are going to be showing that today. And we're going to start by using a graduated cylinder to measure out 70 ml of your regular water. So you have a plastic graduated cylinder, and the proper way, the proper technique will be you use the beaker and you place the water in there, and you place the water in the graduated cylinder, and make sure, even though it's water, we still have to follow safety and put on our goggles, right? And we're going to pour the water in here and make sure it's reading 70 with the meniscus, right? That's the proper technique. So we have 70 ml of tap water at room temperature, and we're going to take a dry styrofoam cup, and we're going to place the 70 ml of water in this cup. And we're going to record the exact volume on your table 4. So we place it in the cup. And we also, to be able to increase the temperature of your insulator, you're going to replace it in a second cup. So now we have, right, we're able to create now a better insulating system. So you have the water in there, and then we're going to hold the thermometer in the center of the water, and we're going to use a stopwatch. And we're going to, you should have a stopwatch or your phones. You're going to be using that, and you're going to be recording. I should have one somewhere here. And you're going to be recording this, measuring the temperature of the water. And this is going to be for, let me see, for 30 seconds, right? So for 30 seconds, you should be holding this in the water, and make sure that, once again, proper way of holding it is at the tip. Make sure that the bulb is not touching the bottom of your cup, but you're holding it in the water, in the center of the water, and you will wait for 30 seconds and you will be recording that temperature. Okay, so your temperature at 30 seconds, it should have that. And then once we're finished with that, we're going to place an ice cube on the surface. And this is a petri dish. We're going to place this. And I'm going to take an ice cube. Put an ice cube and place it there. And we are just going to make sure, as we place that ice cube on a surface or in a sink, you can place it in a sink if you need to, or on a surface. I have a little, dish here where I can just place it in there, and I can clearly see the water. See, it's starting to melt, because you want to make sure that you see that it's melting. And so having something with a flat surface, you're able to see that it's melting. And so once it starts to melt, which is already started, we are going to remove it. And see, it started melting already. And we're going to place it inside the cup, the styrofoam cup. So we see we had it melting already. And once we have it inside the cup, we're going to take the thermometer and we're going to stir continuously until all the ice melts. So you're using actually your thermometer to add some type of outside force to the water, right? And you are stirring and adding that vigorous stirring, adding some heat energy to that water. So you're making sure that your ice cube is going to melt. So we see here, we're going to stir until all the ice cube is melt. Once the ice cube completely melts, then we're going to use the stopwatch once again to time 2 minutes in order to allow the temperatures to stabilize. Record the temperature of the center of the water in table 4. So you're going to make sure the temperature stays constant for at least 2 minutes. And then you're going to record. So you're recording constant temperature at 2 minutes. And you're recording that. So let's look at the tables that you will be using to do that. So we're going to make sure then that we properly record that where it belongs. And here. So we then remove the thermometer and carefully we're going to pour the water back into the 100 ml graduated cylinder. And we're going to record the final volume. So remember, we have an initial volume starting out at 70 ml. And now that the ice is completely melted, we're going to take this water, we're going to pour it back in here, and we're going to take a final volume. So what do you think is going to happen to that volume of the water? We started out with 70 ml. So we added an ice cube and we stir until the ice cube melted. And now we're going to read a final volume. And yes, your volume has increased. It's no longer 70, but for me it is 75, 76, 78. I have 78 ml as my final volume. So that's initial volume. This is final equal, I have 78.0 ml of H2O. And so we have recorded all of that for conservation of heat energy. So we notice that energy is neither created nor destroyed, but it's going to be transformed from one form of energy into another. So here are your tables in which you are recording initial volume of your water and the temperature, final volume of the water and the temperature, and then you are looking at table 5 in which you're recording the mass of your water in grams, and then we're looking at the change in temperature, and then we're doing calculation with heat loss and mass of your ice cube and change in the ice temperature and the heat gained by your ice water in units of joules and the heat used to melt the ice in units of joules and the theoretical heat to melt ice in units of joules. And then you're calculating your percent error. Remember that percent error was given to you, that formula was given to you at the very beginning of the recording, in which we talk about the different techniques that are being used in the physics laboratory, in which is a very simple mathematics that we're always going to have to be accounted for, and in which includes always trying to find out how close or how accurate our laboratory results have been, or how precise our laboratory results are as a whole. For specific heat, we're going to, remember we talk about specific heat, and that's going to be actually evaluating the amount of heat that your material is going to absorb or emit, right? So let's see now if this is going to easily absorb heat or is it going to easily emit the heat. So let's look at the steel bolt, and the first thing we need to do, we need to measure out a string that should be 15 to 20 centimeter long. So you get yourself a ruler and you're going to measure out that string, and you could just cut it with a scissors, and then we're going to tie the bolt with the string. And the purpose of doing this is because we're going to be using the string to suspend the bolt from the water. And as we transfer the bolt from the hot to the cold, so we need to have something to hold it up from. See, like this, right? So that's the first thing we're going to do. And once we have done that, we are going to use a 100 milliliter, once again graduate cylinder. We're going to measure out 150 ml of cold water. And I'm going to take some of this out because I think it's really too cold. So I'm going to take some of this. And so we should have a good amount of cold water in here. And we will measure 150 ml. So as you once again remember, the technique is making sure you use the meniscus and you bring that up to a mark, right? You place it in this cup. Label number 1 should be your calorimeter, and that will be 150 ml. And my water is really cold, but you could just use room temperature water. You're going to let this water sit for a while to gain equilibrium. Okay. And that's that. So we did that for the first time. And then, as you can see, the cups, they are stashed together. There are 2 cups here. See, and this again is to create an insulation. And once we have done that, we're going to record the mass of the water in table 6, and excuse me, I'm sorry. We're going to allow the temperature to stabilize, so that means that you're going to keep the thermometer in there in the center of the water until the thermometer is constant. making sure the thermometer is not reading the sides of your cup. Excuse me, I'm sorry. Making sure it's not reading the sides of your cup, okay? So you're going to be doing that. Once it's stabilized, you're going to record that. Now we're going to use the thermometer once again. We're going to measure out this time 200 ml of water. And this is the local water or tap water. And we're going to make sure that was 100. I'm going to get another 100. And we're going to place this in a larger pot. So I have a larger beaker. You're going to place it in a larger pot at home. And we're going to let that come to a boil. And we are going to make sure that we bring the water to a boil, and then we're going to pour that boiling water into a third styrofoam cup. And so I'm going to get a styrofoam cup, and here will be and I should not have my goggles on my forehead, right? They should be on my eyes. Safety first. And I know we always forget. So we're going to have then your styrofoam cup here. And that water is going to be poured into your styrofoam cup. And once we have got the water boiling, then we're going to proceed to do that. Remember, once again, you're not to touch the stove with your hand, and you're not to touch the beaker or the pot with your hand. You have to make sure that you use something to be able to transfer the water into the cup. And so we're going to use the string. As we said before, the bolt is going to be suspended with the string, and we're going to place the bolt in the boiling hot water. But it must not touch the cup, right? So once I transfer that boiling water into the cup, I'm going to place the bolt in the center of the water. And remember, once again, it should not be touching the sides of the cup. And once that is done, we're going to use the stopwatch to time 1 minute interval. And then we're going to use the thermometer to record the temperature after 1 minute. And we're going to record this temperature in the table 6. Once we transfer the hot bolt into the calorimeter, this is your calorimeter. This one has the regular water, 150 ml that I had before. Then this one will have your hot water. So you're going to be doing this. You're going to hold this in here, and you're going to hold it for 1 minute. And after 1 minute, we're going to take the temperature. Then we're going to proceed to transfer it into the cold water. And once it has been transferred into the cold water, we're going to once again record the highest temperature. The thermometer reads over the course of 5 minutes. So we're going to be recording the temperature and the highest temperature for over the course of 5 minutes. So meaning the interval will be up to 5 minutes. So once you have finished reading that, up to 5 minutes, the highest temperature is what we're going to take to do our calculation. And so that temperature will be the temperature recorded as the temperature that the bolt needed to reach thermal equilibrium. Remember, that's going to be then at equilibrium. The thermal equilibrium is going to be where we have that constant temperature, where the heat then is going to be so the bolt and the water, remember, must reach that same exact temperature. So as they come in equilibrium, right, you're looking for that constant temperature where both of them then is equal. So heat gain equal heat loss, right? That's what we're looking for. And so we're going to record all of these temperature readings from the temperature of the bolt and the steam water, of the hot water and the cold water. And so as we transfer that into the calorimeter, in this table. So you have some calculations to do here. You're recording the temperature of the bolt, then you're recording the temperature of your water. So water and the temperature of the bolt in the boiling water, and then we're looking at that difference in temperature. And then we're looking at the bolt, the mass of the bolt in kilograms, so you must take the mass of that. And then we're also looking at the water of the mass of water in kilograms. And then all of that will be recorded in this table here. So some of the calculations, you will get them throughout the lecture as well, and they also are in the first recording in which I showed you the formulas that we're going to be using. Because we're looking at heat absorb or release, right? And so that heat absorb or release, then we should have found that before. And with a mass and change in temperature, we then can find the specific heat. So the specific heat then, once again, specific heat will be equal then to the heat absorbed or release over the mass times the change in your temperature. So that's the calculation you're going to be doing. So the water is boiling now, and I am going to stir water boil. And where is our bolt? You ready?
Yeah.
So the water is boiling, so I'm going to take the water, the boiling water, and I'm going to pour it into the cup, the styrofoam cup. And then we're going to hold the bolt inside the water for approximately 1 minute, right? And so we're making sure then this water was boiled, and see, I hold the beaker with a glove, and you should do the same thing. Do not hold that with your bare hands. And this is the calorimeter that has the cold water in it. So after a minute, then you're going to transfer that over here, right? So we're transferring from the hot to the cold, and then we're going to determine based on that change in temperature, you know, what happens. So remember again, we're looking at finding the specific heat of this steel bolt. And once we have done all of that, then we're ready to do our calculations, and your experiment is over.